Welcome back, students. Now I am here with the third part for light reflection and refraction. Already I am explaining you about the reflection part, image formation by plane mirror and image formation by spherical mirrors. In this video, I am going to explain you about the refraction. Here you can see an example. When we dip a pencil in a glass of water, from the surface of water it look as that the pencil is bent, but actually it is not. That phenomena is based on the refraction of light. So here are some topics that we are going to cover in the refraction part: refraction of light, laws of reflection, refractive index, refraction through a parallel glass slab, and all these are the topics that are covered by us. First is refraction of light. Refraction of light means the changing of path, the changing of the path or the change in the direction of path when it moves it when it passes through from one transparent medium to another transparent medium, that is known as refraction of light. So refraction is the phenomena of change in path of the light as it travels from one transparent medium to another. Or we can say that change in the speed of light from passing through one transparent medium to another, that is also known as refraction of light. Here I am taking the two actually basically there are the two medias. First one is air and the second one I am taking a glass, rare and denser. So you can see that air is a rare medium, glass is denser, and again the air is rare. Light ray is incident on the glass. That's why it is moves from the rare to denser and it bend in this direction. And now the light rays goes from denser to rare and it goes in direction. So we are drawing the two normal on these points. Now rare optically rare mediums who has the low density and the denser medium are those who are having the high densities. Second one, there are the number of particles in the rare medium are less and the denser medium the number of particles are high. Again, now you can see here, when a light ray moves, when a light ray passes through a rare to denser medium, then it bends towards the normal, and when it passes through the denser to rare medium, then it goes away from the normal. Next topic is law of refraction. The first law is same like of that of the reflection. Incident ray normal at the point of incidence and the refracted ray, they all lie in a same plane. And the second law is for a given pair of media, the light of a given wavelength, the ratio of the sine of angle of incidence to the sine of angle of refraction is constant. That is known as Snell's law. This is the angle of refraction, the angle between normal and incident ray, and the angle between refracted and the normal, that is known as the angle of refraction. So sine of angle I upon my sine of angle R, that is known as that is a constant, and this law is known as the Snell's law. The reason in the first medium it moves through with a high speed, and this is the slow medium or the denser, the speed becomes low. Now bending of light, I am going to explain you with an example. You can see here, this is an plane mirror or any denser medium, you can consider it. In a rare medium the speed of light is c and the refractive index is mu1 denser, the speed of light is b and the refractive index is mu2. I am going to further what is the refractive index. So now you can see these are the rays are coming on this. First ray is reach earlier and it moves in this direction. Second ray after that, and the last ray is reach less. Again you can see, so first ray is bending more, second and the third. This is known as bending of light. Refractive index. So refractive index, the refractive index of second medium with respect to the first medium is defined as the ratio of the angle I upon my angle R, that is known as the refractive index. Because it is just because of the refractive index of second with respect to 1, that's why we are heading the mu to 1. Mu to 1, it means the refractive index of second medium with respect to one medium. Of if we are have to taken the refractive index of the second medium with respect to first medium is also defined as the ratio of the speed of light in first medium upon the speed of light in second medium. If we are taking the first medium as vacuum and air, then the refractive index is called the absolute refractive index, and speed of light in the air is c, and the speed of light in medium is v. So then mu equals to c upon v, that is known as absolute refractive index mu m equals to c upon v. Now refraction through a parallel glass slab. This is the parallel glass slab. This is the rare medium A, denser medium B, and the rare medium A. And let me consider the refractive index of the second medium is mu, and the length of or the width of the parallel glass slab is t. If any ray is incident, it goes in this direction. Basically, it has to, when we know that the light travel in a straight line, so it goes in this direction, but due to the refraction it bends in this direction and go after from the denser to rare medium, it goes in this direction. So this is the actual path, but the light ray goes in this direction. We have drawn the two normals on the two surfaces. So here, for the first time, when the rare to denser reflection is here, so light ray come here, this is the angle of incidence I1, we draw a normal. This is the actual position, but the light ray bends in this direction, and it is the angle of reflection R1. Number 2, now यहाँ पे I2 is here, ठीक है, I2 is the angle of the incidence for the second surface. We are going again draw a normal here, and now this time the light ray goes from denser to rare medium. It moves away from the normal, and it goes in this direction. So sine 1 upon में sine R1 equals to A mu B. A mu B means the refractive index of B with respect to A. And second, if we are going to ask about the second refraction, so that is the B mu A equals to sine I2 upon में sine R2. But mu AB and W mu equals to 1, it means the condition of the refractive index for these two refraction equals to 1. So we are putting the formulas here. Tips, you can see here some tips I've already mentioned, you can read in this video. Of these are the refractive index sum of the medias with respect to vacuum. These are the suppose water refractive index of water is 1.33. Actually, this is the refractive index of water with respect to vacuum. Now the next is refraction by the spherical lenses, and in the reflection part we are study about the spherical mirrors. So in refraction part we are going to study about the spherical lenses. Lenses whose reflecting surface are spherical are called spherical lenses. First one is the double convex lens. Double convex lens, there is the bulging outward surface when we make a lens with the bulging outward surface, which is the thicker in middle and as comparison to the edges. So you can see here, this is the double convex. This is bulge out first surface, bulge out second surface. From the edges it is a thin, and from the middle it is a thick. Number 2, this is a double concave lens. Concave lens, it means this is the first concave position, and this is the second concave, and this is thin in middle, and this is the thick in the edges. This is the plano-convex, plano-concave, convexo-concave, and concavo-convex. These are the some type of the spherical mirrors. Now we are going to study about some terms that are related to the spherical lenses. First principal focus. The first principal focus is point on the principal axis of the lens, at which if an object is, you can see, I'm going to explain you with the diagrams. Okay. If the light rays coming from the first focus and the light rays become parallel after reflection, that is known as the first focus, and the length through the center of the center of the lens is this point. From the center to the f1, that is known as the focal length f1. You can see here also these light rays are look like that they are coming from the focus, but actually they are coming from this point, and they are goes parallel to the principal focus, and this is known as the principal focus 1. Second principal focus, now So you can see here, when the light rays are parallel to the principal focus and when they are passes through the lens and meet at a point f2 of second side. Okay, first side, through the focus the light rays are incident on the lens and they become the parallel to principal focus. But in second case, parallel lines are come on the lens and they are met at a point f2, that is known as the principal focus f2. Convex lens mn, that is the O point, that is the midpoint. Now you can see, so optical center, O is known as the optical center of a lens. C similarly, so C is the center of curvature for this. If we are going to cover this spherical, this is the one part and this is the second part, so that's why the lens has the two center of curvatures. First center of curvature for this surface and second center of curvature for this surface. Similarly for the concave lens also. Third, radius of curvature similarly as of the distance between the optical center and the C is known as the radius of curvature. Principal axis similarly, principal axis, what is the principal axis? So the line joining the center of curvature and the optical center, these are known as the principal axis. Now when the light rays are coming parallel to the principal axis, they all are gone from a point that is known as the f2. We are already discussed about it, f2, and this is the focus f1 and focus f2. Now for the concave lens, for the concave lens, you can see the light rays are not actually made, but they are appear to meet. That's why this is known as the f2 and this is known as the f1, f, and the distance between optical center and f, that is known as focal length. Similarly, here also r equals to 2f and aperture is the diameter of the reflecting surface. Now the rays to be considered for drawing the ray diagram as similarly. Okay. If any rays come parallel to principal axis, then it goes away from the focus. For the concave lenses appear to be go from the focus. Second, if any rays come through the principal focus, then it after the refraction it becomes the parallel to the principal axis. Similarly for the concave lens. Third, if any ray is come through the optic center, now from the optic center, then it goes away in the same direction without any deviation. Fourth, now image formation by a convex lens. When object is at infinity, light rays becomes parallel to the parallel rays are coming from the object because the object is at infinity. That rays are gone from the focus f2 and the image is formed at the focus f2. The position of the image at f2, image is real and inverted, size of the image is very small. When the object is placed between the C and the 2f1, you can see here C1, it means the center of curvature, that is also mentioned here as the 2f1, f1 and the 2f1. Beyond the 2f1 we are placing the object. One ray is taken the parallel to the principal axis, it goes away from the f2 and the center. Second ray is taken by the optic center, they are meet at this point, so image formation is here between f2 and 2f2. Real and inverted image. Inverted, you can see pointing upward, pointing downward, so image is inverted and smaller than the object. When the object is placed at 2f1, so similarly at the center of curvature, two rays are taken, so object is at 2f1, so image is formed at 2f2 of the same size and real and inverted. When the object is between 2f1 and f1, then image formation is at beyond the 2f2. When object is at f1, then the image formation is at infinity. First ray is taken. Similarly, in the two rays, object is image is formed at infinity. Last, when the object is between O and f1, So it makes an virtual image. You can see here now it makes an virtual image, virtual and erect image on the same side of the object and larger than the object. Now similarly make a table. Through this table you are able to learn all the part of the image formation by a convex lens. Now image formation by a concave lens. So when the image object is placed beyond the 2f1, first ray is taken parallel to the principal axis and it goes away from the focus. Second is taken as the from the optic center. So image formation is between O and f1. Now sign convention is same like that of the mirrors. So this is, you can see the right side image distance are positive and the left side image are negative. Upward direction are positive and the downward direction are negative. Same for the concave lens also. Now the lens formula. So I'm going to explain you about the lens formula. See, this is the object between the f1 and 2f1. I have taken an object. First ray is gone parallel to the principal axis and it goes from the f2. Second, the optic center and image formation is beyond the 2f1. So the distance from the optic center to the image, that is known as the image distance v, and the optic center and the object distance is known as the object distance f, and the length f, focal length f. You can see radius of curvature r also. So lens formula is 1 upon maybe minus 1 upon u plus equals to 1 upon f, and the mirror formula is 1 upon maybe plus 1 upon u equals to 1 upon f. That is the difference, that there is a minus sign for the lens formula. Linear magnification as like that of the plane mirror also, as a mirror also, magnification is size of the image upon my size of object, but we are not putting the minus sign here, that is the put in mirror. So there is a v upon my u. Magnification in terms of v and f, the f minus v upon my f. Magnification in terms of u and f, the f upon my f minus u. Power of a lens. Power is what is the power of lens actually? Power of lens is the ability to bend a ray light falling on it, and it is reciprocal of the focal length. So P, it is denoted by the letter capital P. So P is equals to 1 upon F, and F is in meter. So the unit of the power of lens is known as diopter, and it is denoted by the letter D. P equals to 1 upon F. Thank you so much. Now your chapter 10 has been completed for the class 10.